ನಮಸ್ಕಾರ. ಡಿಜಿಟಲ್ ಲರ್ನಿಂಗ್ DCEಗೆ ಸುಸ್ವಾಗತ. In this video, I am going to present you BSc Mathematics 3rd semester, paper 3, groups, properties of coset decomposition, theorem 3 onwards. If H is any subgroup of G, then HH is equal to H is equal to HH, where small h belongs to H. Proof. Let H belongs to H, we shall show that HH is equal to H. Let H1 belongs to H be an arbitrary element. H belongs to H and H1 belongs to H implies that H1 H belongs to H, but H1 H belongs to the coset HH. Therefore, the coset HH is a subset of H. Let us treat this equation as 1. For H1 belongs to H, H1 is equal to H1E, which is equal to H1 H inverse H, because E is nothing but H inverse H. Then this is equal to H1 H inverse into H by using associative law, and that belongs to the right coset HH. Therefore, H1 belongs to H implies that H1 belongs to the coset HH. Therefore, H is a subset of HH. Let us treat this as equation 2. Now by equation 1 and 2, HH is equal to H. Similarly, it can be proved HH is equal to capital H, means the set H. Now let us pass on to theorem 4. If A and B are any two elements of a group G and H is any subgroup of G, then HA is equal to HB implies AB inverse belongs to H, and AH is equal to BH implies A inverse B belongs to H. Proof. The necessary part. By the data, the coset HA is equal to HB, where H is a subgroup of G and A, B be any two arbitrary elements of G. Let A belongs to the coset HA, since HA is equal to HB, so A is also belongs to HB, which implies that A B inverse belongs to coset HB into B inverse. Because A belongs to HB, therefore AB inverse belongs to HB B inverse. This further implies AB inverse belongs to HB B inverse. This implies AB inverse belongs to HA. See, by using associative law, B and B inverse, if we combine together, it is nothing but an identity element. So, AB inverse belongs to HE. That is nothing but AB inverse belongs to H, because HE is H. Sufficient part. Since it is nothing but the converse of the theorem, let H be any subgroup of a group G and let AB be any two arbitrary elements of G, such that AB inverse belongs to H, and we have to show that HA is equal to HB. Means these two cosets are equal, we have to prove. AB inverse belongs to H implies HAB inverse is equal to H, which implies HAB inverse B is equal to HB. Further, this implies HA into B inverse B is equal to HB. That is equal to HAE, because B inverse B is equal to E. HAE is equal to HB. This implies HA is equal to HB. Both the cosets are equal. Hence HA is equal to HB. AB inverse belongs to H. Similarly, HA is equal to BH implies A inverse B belongs to, hence the theorem. Theorem 5. Show that any two right cosets are identical or disjoint. Similarly, we can prove left cosets also. Any two right cosets are identical or disjoint. Proof. Let us consider HA and HBB, any two right cosets of H in G. If HA intersection HB is a null set, then we say that HA and HB are disjoint. If HA intersection HB is not a null set, then there is an element X belongs to HA intersection HB implies X belongs to HA and X belongs to HB. So we have HA is equal to HX. Treat this as equation 1 and HB is equal to HX as equation 2. By these two equations, HA is equal to HB. Theorem 5.1. Show that any two left cosets are identical, either disjoint. So the proof is similar to the previous theorem. Theorem 6. Let H be a subgroup of G, then show that there is one-to-one correspondence between any two right cosets of H in G. Proof. Let us consider a mapping F from HA to HB, and let us prove by taking this diagram, that is proof. Let HA and HB be any two right cosets of H in G. Define a function f from HA to HB by f of HA is equal to HB. Means the image of HA is HB. First we have to show that f is well defined and 1 1, and then f is onto to prove one-to-one correspondence. If f is well defined and 1 1, let us prove this one. Let x comma y belongs to HA, which implies x is equal to H1A and y is equal to H2A. X is equal to y implies that H1A is equal to H2A, which implies H1 is equal to H2A. A get cancels here. Further, this implies H1B is equal to H2B. That implies f of H1A is equal to f of H2A, which implies f of x is equal to f of y. Means we took x is equal to y and proved f of x is equal to f of y. Therefore, the f is 1 1. Then on to, let us consider x dash belongs to HB implies x dash is equal to HB for some h belongs to H. Then there exists an element x is equal to HA in HA such that f of x is equal to f of HA, which is equal to HB, that is equal to x dash. Means image of x element is denoted by x dash. Theorem 6.2. Show that there is one-to-one correspondence between the set of all right cosets and set of all left cosets. Proof. Let us consider this diagram where f is defined from R to L set HB. HB is nothing but A inverse H. Now let us take R is equal to A belongs to G set, which is the set of all right cosets of H in G, and let L is equal to A such that A belongs to G be the set of all left cosets of H in G. So here we have defined a mapping F from right cosets to left cosets by f of HA is equal to A inverse H. For this theorem also, we have to prove that f is well defined and 1, 1. So to prove this, let us consider HA is equal to HB, which implies AB inverse belongs to H. That implies A belongs to HB and A is equal to HB for some H in G. Then A inverse is equal to B inverse H inverse belongs to B inverse H. Further, this implies A inverse H is equal to B inverse H. Therefore, f of HA is equal to f of HB. F is onto let A inverse H belongs to L implies A belongs to G. There exists HA belongs to R such that f of HA is equal to A inverse H. Hence, there is 1-to-1 correspondence between the set of all right cosets and left cosets. Thank you.